we're going to look at one sample hypothesis testing, and we're going to do the classical method when sigma is known. So we're going to recognize the different steps that go with the hypothesis testing and its logics and carry it out using critical values and a thing called rejection regions. So we're going to look once again at the reasoning of tests of significance, stating hypotheses, how significant tests work. And we went over type 1 and type 2 errors. What we're going to concentrate on here is critical values and the rejection regions and the idea of statistical significance. What we looked at before is we had p-values. We started the problem with a significance level, and of course we're in a right, left, or a two-tailed test. So I'm going to first concentrate on a right-tailed test where we think the mean has increased. So we'd have that all our conditions are met. So we've got our sampling distribution of the sample mean is approximately normal, and we know what sigma is, so we can literally use the standard normal table to find probabilities and to get p-values. So the second thing is that we're given a particular significance level. So for our example here, let's pick the significance level of 0.05. And your third step would be to calculate the test statistic. So you'd get some number for the test statistic. So what we do is we're in a right-tailed test, so we know that this is alpha. This darkened area right here is alpha, the probability under that curve. And we had our test statistic, and our test statistic was Z naught. It would be here. And what we did is, remember, for a right-tailed test, we found out the probability of Z being greater than this test statistic is what we called our p-value. That means this red area right here. And our criteria for rejection was if the p-value was less than alpha. And look, the p-value, our alpha is the blue, our p-value is the red. That p-value is definitely less than alpha. Now, how critical values work is this way. Everything would still look the same. Steps 1 through 3 would be the same. So this is our p-value method for a right-tailed test, and this is the classical or finding critical regions. So steps 1 through 3 remain the same. What changes is step 4. What we do in step 4, instead of looking at probabilities, we're going to look at the number line. So how Z naught is a number on the number line, we're going to find something called a critical value. The critical value that goes with the probability of 0.05 being to the right of it. So we could use our standard normal table to find that. Our standard normal table only goes to the left. So if I wanted to find this, so our standard normal table only gives us these probabilities. But if I wanted to find the probability, the z-score, the critical value such that 0.05 is to the right, it's the same thing as finding this critical value over here, 0.05, and just take the positive value of it. So if I look for 0.05, I don't see it. I see it something a little bit greater and something a little bit less, remember? So 0.05, equidistance, that's how we got that negative 1.645. So for a right-tailed test, the critical value would be a positive 1.645. So that means the critical value here is 1.645, and my test statistic is greater than it. So what we find out in this is we get our critical value based on alpha, and then our criteria for rejection. Well, if we're in a right-tailed test, if our critical value, if our test statistic is greater than our critical value, we reject the null hypothesis, because that would make our p-value less than our alpha when our test statistic is greater than our critical value. And then we would reject, and then both of these, after we do that, is you state your conclusion in the context of the problem. So let's look at what a what a left-tailed test would look like. So in a left-tailed test, we're now looking here, okay? So we're no longer in this right tail right here, right? We're now looking in the left. So my alpha being 0.05, so these would change here, and we'll see how this changes for us too. But here's here's our alpha for a left-tailed test. It's going to be over here. And we'd get our test statistic. And our test statistic, let's say, was here. Okay. And so we'd get our p-value. If you remember how we got the p-value, that's step 5. Step 4 is getting our p-value. The probability z is less than our test statistic if we're in a left-tailed test. So our p-value would be this right here. And 5 is always the same. If my p-value is less than alpha, I'm going to reject the null hypothesis. So in this case, once again, we would reject the null hypothesis. Now in the classical method, we've done step 1 through 3, so we got all this information, and we even know at the start of the problem what my critical value is going to be, because I know what alpha is. So I know that my z critical for an alpha of, let's say, 0.05 is going to be negative 1.645. So my critical value would be right here. So my criteria for rejection for a left-tailed test, remember we're in a left-tailed test, mu less than mu naught, because we're using these same 3, it would be if my test statistic is less than my critical value. I would reject the null hypothesis. So what we're doing is we're using the number line, we're getting a critical region. This right here is called the critical region. Any number less than my critical value will tell me to reject the null hypothesis if I'm in a left-tailed test. And we saw it for a right-tailed test, that the critical region would be in the right tail. So now let's look at a two-tailed test. And again, I'm just going to take an alpha of 0.05. Now what we did here is once we got our test statistic, to find our p-value, step 4, if you remember, the p-value, if my test statistic was greater than 0, to find the p-value, it was 2 times the probability z was greater than that test statistic. But if my test statistic was a negative number, the p-value, the way I'd find it, was 2 times the probability z was less than that negative test statistic. Remember, those were the 2 different ways. So with this, what we find out is in the classical method, for 0.05, we have to divide this by 2. This would be 0.025 here, because at the start of the problem, we never know if our sample would be either in the right or left tail. We get the critical value for 0.025, and if you remember what that was, when I had alpha, it was 1.96, and this was negative 1.96. So what happens here is now this is my critical region, anything less than negative 1.96 and anything greater than 1.96. So for the classical method for step 4, you'd have 2 critical values, plus or minus 1.96. And the way that we reject or do not reject, well, this one is always if the p-value is less than alpha, you reject the null hypothesis. But for this one, if my test statistic is greater than 0, is positive, then to reject, my test statistic has to be greater than the positive critical value. Or if my test statistic is negative, then I have to see if my test statistic is less than that negative critical value, because now you're going to have 2 critical values. So if my test statistic had been, let's say my test statistic were here, Z naught, then I would have went to this one and I would have seen if Z naught was less than negative 1.96, and I would reject the null hypothesis. Now you're saying, oh man, I have to find all those critical values. This is really, really hard. You know, that normal distribution scares me or something. Well, don't worry. Because we're in the standard normal distribution, those critical values won't change for our situation. We always use significance levels of 0.05, 0.01, and 0.1. So for a left-tailed test, your critical value at a 0.05 significance level will always be negative 1.645. Now for a right-tailed test at a significance level of 0.05, your critical value is going to be 1.645. And for a two-tailed test at a 0.05 significance level, your critical values, you'll have two of them, will always be plus or minus 1.96. And the same for 0.01. For a left-tailed test, it's always negative 2.33. For a right-tailed, 2.33. And for a two-tailed, you have two critical values. You have to look in two different places. And it's plus or minus 2.576. And then for a 0.1 significance level, you'll have your left, negative 1.28 is your critical value. For the right, 1.28 is your critical value. And for the two-tailed, it's plus or minus 1.645. And if you note, these alphas and these right here, these are how we found confidence intervals. So our confidence intervals and hypothesis testing for two-tailed tests, the way that we did confidence intervals, they actually will let us know if we would reject or not reject the null hypothesis. So looking at the 6-step process, it doesn't look very different at all for steps 1 through 3. So you have to state the null and alternative hypothesis. Now remember, before you even do any of this, you have to make sure that all conditions are met so that you can do a hypothesis test. So state the null and alternative hypothesis after you make sure the conditions are met. State the significance level. Calculate the test statistic. Remember how many standard deviations that sample mean is in the null hypothesis distribution. So the calculation would be your sample mean minus the null hypothesis mean divided by that standard deviation of your null hypothesis, that standard error. Then determine the critical values. Well, this is how you determine the critical values right here for a right-tailed test. This is how you find your critical value, that Z sub C. You're given a probability in finding the Z-score that goes with it. But what's nice is we have that. You don't have to determine them because you'll have this little handy thing ready to help you find the critical values. And I'm going to show you another way that you can find the critical values also, that you don't even have to have it written down if you have the student's t-distribution. So with the student's t-distribution, at the very bottom, you see this one-sided and two-sided? Well, this is how you can use your student's t to actually know what the critical values are. One-sided means your alternative is either going to be mu is less than mu naught, or your alternative is mu is greater than mu naught. This is where you would find your alphas. And so at a 0.05 significance level, for a right-tailed test, it's positive 1.645. And for the left-tailed test, it's negative 1.645, which is exactly what you saw in your PowerPoint. For a 0.05 significance level, your left-tailed test is negative 1.645, positive 1.645 for a right-tailed test. For a 0.01 significance level, for a left-tailed test, it's negative 2.33 and positive 2.33 for a right-tailed test. Well, there it is. 0.01 is your alpha, and 2.33, if you round that to the second decimal place, it would be 2.33. How we would find that? So for a 0.1 significance level, for my alpha of 0.1, it'd be 1.28, which is exactly what we have here on the PowerPoint, of 1.28 and negative 1.28. So the left tail is always going to have a negative number and the right tail a positive number. And now how do we find the two tail? If I just wanted to have my student t distribution with me, well, I'd go to the two-sided right here probabilities, or the alphas. You Could actually put alpha here if you wanted to. So for a two-sided, that is, my alternative is mu just doesn't equal a value. And I'm looking at 0.05 significance level. Well, it's 1.96. For a 0.01 significance level, it's 2.576. And for a 0.1, it's 1.645. Those things, if you remember, those are exactly the alphas for our confidence intervals. Remember, 1 minus alpha gave me the confidence level. So 1 minus 0.1 is the 90% confidence level. And we knew that the critical value is 1.645. So that's where the confidence intervals sort of relate to hypothesis testing. That's sort of they do. But anyway, we have the numbers here for you. So you don't even have to think about it. Now, once you know what the critical value is, you determine it. Then, for a right-tailed test, that is, my alternative looks like mu is greater than mu naught. I see if my test statistic is greater than the critical value. If it is, I reject the null hypothesis. For the left-tailed test, mu less than mu naught. If my test statistic is less than the critical value, which of course that critical value will be a negative number, I would reject the null hypothesis. And then for that two-tailed test, mu not equal to mu naught, if my test statistic is less than my critical value, I would reject, or if my test statistic is greater than my critical value. I actually split that up, if you remember. I said if my test statistic is positive, then just look at this. And if my test statistic were negative, just look at that, because that's how it would work. And then if you reject or not reject, then you interpret your results in the context of the problem. So looking at that problem that we did with the p-value method, with the NHANES survey, the mean height of adult men was 69.7 with a standard deviation of 3 inches, and that sociologists believe that taller men may be more likely to be promoted to positions of leadership. So the mean height of male business execs may be greater than the male height of the entire population. So we have this sample of 100 we took, a random sample of 100 businessmen. Their mean height was 69.9. That was our sample mean. We want to test the sociologist's claim that the male business execs are taller on average than the general male population. Well, having a random sample of 100, first of all, that tells me that I am doing this hypothesis test, that my conditions are met, because I can evoke the central limit theorem and my sampling distribution is approximately normal. So, of course, we always assume that 1 and 2 conditions are met, that my sample was obtained from a simple random sample or a randomized experiment, and my sample size is small compared to my complete population. So now I can say my null hypothesis and my alternative. We're going to assume that heights of the businessmen are 69.7, but we want to test the sociologist's claim that businessmen are actually taller. So we have to give proof that our mean is actually greater than 69.7 for businessmen. And since all my conditions are met, I now can describe completely this null hypothesis. It's going to be normally distributed with a mean of 69.7 and a standard deviation of the sampling distribution, that standard error of sigma, which is 3, divided by the square root of the sample size. So let me make that a little bit neater. So we have our null and alternative. We have our alpha. Alpha is given to us as 0.05. And actually, we even now know, since it's a right-tailed test, exactly what the critical value is going to be. So for 0.05, right-tailed test, it's 1.645. Kind of keep that in the back of your head. And now we're able to calculate the test statistic. The test statistic is going to be that sample mean, the 69.9, minus the mean in my null hypothesis distribution, the 69.7, and divide that by that standard error, 3 divided by the square root of 100. And when I do that calculation here, I get 0.67 as my test statistic. Now, we know that the critical value is 1.645 because our alpha is 0.05, and for a right-tailed test, that's what our critical value was. Now my test statistic was 0.69. My critical value is 1.645. My criteria for rejection is that test statistic has to be greater than my critical value, and it's not. So we do not have enough evidence. We do not reject the null hypothesis. So at a 0.05 significance level, there's insufficient evidence to support the sociologist's claim that the male execs have a greater mean height than adult males in general. And in the PowerPoint, I give a left and a two-tailed test example also, using the critical value or classical method of hypothesis testing. Well, I hope this was helpful, and thanks so much for watching.